Hi and good afternoon, everyone. I'm Achintya Paradkar, and Aman had already given a quick introduction. I would just like to rephrase the education part to motivate that I started as a bachelor in mechanical engineering, and I even worked as a design engineer for a few years, and then a point came when I realized that I wanted to go for research, and then I completely switched my track and then went for nanoscience for my master's. And now I'm pursuing my PhD in experimental physics. So from this track, you can clearly see that it's completely, what do you say, all kinds of weird turns that I've taken in my career. And despite all of these shifts, this has been a really enriching experience. And usually I see this in many bachelor students that they want to change their track, or they want to jump into a new emerging technology, let's say quantum computing, for example. But then they are hesitant that, oh, I may not have the relevant background, or I may not have the necessary skill sets to go into this. Should I or should I not? It's too unconventional. And then they stick to the conventional engineering approach. And this would be the aim of my talk, to kind of break that barrier towards entry into this field and motivate you that you can actually be a part of this. And this is something very much relatable to what you already have learned in your courses, and what would be a nice uh, roadmap towards actually being a part of this cool technology. So with that, let's start with the buzz of the word quantum. Aritra has already given us a very nice conceptual understanding of the phenomena of quantum, with this nice vada pav and modak analogy, which made me kind of hungry. But yeah, we learned the concept in a very much fun way. I would like to zoom out at this point and take you towards a more practical side of things. So conceptually, now we know what the physics is, and how do we mathematically model it, and what kind of applications they have. Here I would like to look at it from a more technological perspective. So normally we see this buzz about quantum computing in these kind of sci-fi movies, or usually in conversations where people just throw the word to either sound smart or to make it much appealing. And it actually has a more counter effect. It's counterproductive in the sense that people start to think that, oh, it's something very alien, it's something that is unrealistic, something uh, that is only available in those high facility military equipment, not something that is available at our homes. And today I would like to break that myth, which we typically have, that quantum is only in sci-fi movies or in these cool research facilities, and not in our daily lives. So I would first like to start with the quantum revolution. So the first quantum revolution, I think Aritra already briefly touched upon it, started after the World War II period, or somewhere during that period, where people like Einstein, Enrico Fermi, and these scientists came up with this quantum mechanical model, Bohr and Schrodinger, and all these people. And they found out these different phenomena that could be used for technological applications. And then we had all these technologies like transistor. So your computers, your smartphones, USB drives, all of these are based on the basic principles of quantum mechanics, without which these technologies could not have been possible. So quantum phenomena, for example, wave particle duality, discretization of energy levels, barrier tunneling. So all of these technologies make your transistors and your computers possible. Lasers, for example, for that, again, you need quantization of energy. LEDs, again, there are energy levels involved. All of these can only be explained with quantum mechanics. And then finally, your GPS. So every time you're opening your Google Maps and navigating at different places, it is always an atomic clock sitting in some satellite high up in the sky that is enabling these super precise 5-meter accuracy precision for your Google Maps. So this
Sorry to interrupt. I think there's some obstruction to your slides. The entire screen is not being shared. So there is your title, like the first quantum revolution, is getting obstructed by some.
Ah, is it okay?
Yeah.
Is it okay now?
No, actually, maybe exit and then the okay. So it shifted, but there is still some obstruction. I think when you right click, something is happening. So maybe.
Oh, this is weird.
Uh,
Maybe I'll stop sharing and reshare.
yeah, exactly. Yeah.
Yeah, that would work. Let's see. These things
Exactly right. It's
keep
what is a
happening.
Zoom meeting without?
Yeah, absolutely. So yeah, is it fine now?
Okay, it is fine now. Good, thanks.
Okay, cool.
Go on.
Yeah,
Yeah.
thanks a lot, Rishi, for bringing that up. So, okay, let's continue. So, yeah, so we see that all these technologies are already existing, which is built on quantum revolution, which is built on quantum technology. So, then what is this buzz about quantum technology that is coming up? That would be a second quantum revolution. And that predominantly comprises of four major branches, which are quantum computing, which Aritra just explained, quantum simulation, which is related to quantum computing, but you don't compute, you simulate to the ground state and find an optimum solution to a specific problem. There's quantum sensing, in which I do my PhD, that is to sense different physical parameters, for example, force or acceleration, to precisions that go to zeptonewton or let's say 10 to the power minus 21, 24 newtons. And these kind of high sensitivity sensors can be used for various applications and open doors towards regimes that have not been known before. So for example, in simple technological applications, it can be used for navigation, or for geo imaging of the earth and the magnetic field therein, or it can be used for probing into fundamental physics. So for example, detecting gravitational waves or detecting dark matter and understanding all these different cosmological models that we have, or even basic particle physics models that we have. So to give you a small example of quantum sensing, these Large Hadron Collider, LHC, where you find all these Higgs boson and all these fancy particles being detected. These detections are only possible with such quantum sensors. So you have some kind of superconducting cavities or various other sensors that work at ultra sensitive regime. And then you have quantum communications. You might have heard this as well in the news, that China, USA, and now even India is jumping into it, which can be used for making communication extremely unbreakable. So the laws of physics will ensure that your communication is completely encrypted. So these comprise your second quantum revolution. And this is where the whole buzz about the technology comes from. And these different technologies are based upon higher phenomena of quantum mechanics. So we saw energy levels, we saw quantization of electrons. Here we use superposition, we use entanglement. So certain principles which Aritra was talking about. We use spin polarization of particles. So these are some advanced phenomena that we implement to develop some advanced technologies. Okay, so all of these are good in theory, but then we always hear about these buzz of nanotechnology and quantum technology, but like, where is it in reality? We always make these promises, right? Yeah, it's not up to the mark today, but 5 years later, 10 years later, it will be. And we don't see them happening. So what's the tech status of quantum technology today? So first of all, I mean, straight off the bat, I would say that there are lots of companies who are already pouring money into quantum technology. And this itself is a guarantee. Because if you're putting millions and billions of dollars into something, the technology has to be working. There has to be some good promises. Otherwise, just a second, let me turn on my pointer. Yeah, you see Honeywell, you see Amazon, you see Microsoft, you see Intel, you see IBM, you see Rigetti, Google. All these big companies are already there, and you might have seen them in the news as well. And there are some companies, again, in Europe and also coming up in India. so which are doing a lot of research into this technology. So these are the corporate private companies. Additionally, governments themselves are spending a lot into developing quantum technology. So if you look at the chart, you can see most of the companies are putting money that are in the orders of, say, billions of US dollar. So all of these figures are in millions. So they are spendings in millions of US dollars. So that's a correction over here. So you can see that even India is not too far off. The current spending of India is around, say, 1 billion US dollar, which is quite in par with the European Union, United States, UK, and even France. And it's already almost in top 10, top 7, right? So we are already promising a lot of money. So then the question is, how is this money going to be spent in order to develop some technologies in India? So for this, the nation, the government of India has developed this national mission for developing quantum technologies that was announced in the Union Budget of 2020. Maybe you might have heard of it, where 8,000 crores, roughly a billion US dollar, will be spent for a period of 5 years. How? It will be used into the research at various organizations, which are IISc, Raman Research Institute, Tata Institute, IISER Pune, Mohali, and various other places as well, IIT Bombay, and then certain government organizations like ISRO and DRDO. For this, there's a separate panel comprising of various scientists and industrialists who are enabling, who are making sure that these kind of technologies can be enabled both in theory and in practice. And one of the top funding is going for quantum sensing and computing. Apart from these companies, apart from these institutes, there are certain companies, some startups that are already coming up. So Boson Q and Q Labs are already showing some promises. And these are all Indian-based companies, right? So this itself is quite promising that yes, we have research institutes researching the technology, and we have companies who are already investing. And even IBM and other big techs are thinking of bringing or actually at least developing some technology in the Indian market. So now that we know that, okay, there's this, there are these 4 branches of quantum technology, and people all over the world are pouring money into it. How does the roadmap for this look like? So, as I said in the very first slide, the first quantum revolution that went from transistors and lasers and so on, the last of that was atomic clocks. And atomic clocks are used in satellites. They enable navigation, they enable your Google Maps and everything, and even for extreme precise military application. So atomic clocks are a type of quantum sensors, and they opened up this huge branch of quantum sensing. So the next technology that will be that can be logically developed in an immediate future would be quantum sensors. They're already out in the market, and the market is quite growing. The next would be quantum communication, which has been now shown for certain kilometers of encryption of data. And then if you can scale it up to thousands, we already have success there. And finally would be quantum computing. So in terms of its tech readiness, so this was the very point with which I started, right? Where are we right now in terms of tech readiness, or in terms of its current status? So for atomic clocks, the physics is quite well developed. The engineering is still developing, and it's quite good. And the market is emerging. So atomic clocks, you can already see that there are companies, there are already government who have already invested a lot into this, and now are moving towards quantum sensing, for which the physics is developing. And I would say it's really there in order to actually go towards engineering, which is now emerging. The market is still nascent. So it is expected that in the coming 10 years, the market will actually start to boom. There are certain market reports. I do not like to make big promises, so I don't show them over here, but there are some what do you say, research that says that the market for quantum sensing is quite good. And then for quantum communication, it goes a bit down and down and down. So you'll see that the physics is still emerging, engineering is not so well developed, and the market is not there. And similarly for quantum computing as well, the physics and engineering still need to improve, and with that the market will come later on. So this is the roadmap, and then you can see that quantum sensing comes first, then communication, and then computing. And of course, like, this is not very watertight. There will be some concurrent developments, and some technology of quantum computing will be used for sensing, vice versa. All of that will happen. So this is with the quantum roadmap. Now you can see that, as I showed in my previous slide, the physics is first developed, and it's always highly developed, and then followed by engineering, and finally by market. So the flow goes such that the theoreticians will come, they will create some model, some basic mathematical model, and show with some basic equations that it can be possible. The experimental physicist will come. So if you follow Big Bang Theory, it's like, you know, Sheldon making some equations, Leonard taking it to the lab, and then he will be doing it doing some lab proof of concept that yes, whatever the equations say, they work in practice. And it will be a very, what do you say, very tiny result, very small and vague result, but it will be still a proof of concept. And now comes the engineers. So they say, yeah, okay, you get something. So, you know, like normally as a physicist, we say that, okay, the theory expected 80 and we are getting 18, but you know, the order of magnitude is still the same. So let's call it a win. Engineers don't work like that. You can already vouch for that. So with engineering, precision matters. And for that, you need to optimize the technology. And then comes all the people with their expertise in various fields who will find out the problems in a more meticulous manner and pinpoint them so that they can troubleshoot it. And slowly, the technology can then be scaled up by reducing each and every problem. So just like you saw with semiconductor technology, when the first transistor was built, it was super big. You could hold it in your hand. It was that big, but it was a proof of concept. They won the Nobel Prize for that. But then slowly, then came vacuum diodes, and then came CMOS technology. All of that was the job of engineers. And now you have all these core i3, i5, i7. Similar trend quantum computing will be seeing. And that is where you people come into picture. So engineering actually plays a very crucial role in quantum technology, even though it is quantum and it sounds like physics. Now it is moving towards engineering. That's the crux to be taken from here. A quick stack of the technology. So you can see here, I'm laying out certain quantum fields. So sensing, information, simulation, communication, computation. All of them will have two aspects: the control aspect, which comes from the model, from the theory, and then the engineering aspect, which will develop the hardware. So with that, you will have the theory and the design initially coming up, and then slowly you will fabricate certain chips. You will show some, yeah, they work. Then the control electronics will be developed, then the packaging, validation, prototype. Those people who are from electronics background, they already know what I'm talking. So this is how every technology evolves, right? Not just quantum. So currently for quantum technology, if you specifically talk about quantum computing, the theory and design are there. Now we are working with the fabrication of the chips. We fabricate, we show that, yeah, the quality factor is low, something needs to be improved in the material and the fabrication techniques, so on and so forth. And already the control electronics is being worked with. So we are somewhere over here, stack 2 and 3, let's say. All of these, commercialization will come later on. But herein actually lies the core engineering problems. So what are those? So yeah, quantum engineers wanted, right? So they are wanted to actually solve these engineering problems. I see that there are actually very few mechanical engineers in the audience, but still, you can imagine, right, that for any technology, you need the hardware. And the hardware only comes with mechanical engineering. So anyone who has some mechanical background can develop the hardware, solve the challenges of materials, cryogenics, magnetic shielding, all of those things which we actually already learn, like thermodynamics and fluid mechanics in the courses of our engineering. Then comes electronics. So for quantum computing, uh, you, uh, you can you can just simply think of it like a microwave system. So all of these qubits, these quantum bits, they work in the gigahertz regime, which is the microwave regime. And then all the microwave, the analog electronics which you study in your courses, all of that will come over here. So your signal mixing, your multiplexing and modulation of signals, all of that, your low noise amplifiers, control systems for your signals and everything, all these things become super crucial. And now even FPGA, which is a part of embedded systems, is taking up a lot of attention. Why? That is because, so even Aritra touched upon it, that we need large number of qubits, right? So he was talking about this 2 to the power n, where he was saying that the more the number of qubits you have, the higher advantage you get. Currently, we have like say 20 qubits, 50 qubits, they do something, but nothing super promising, nothing extremely advantageous. And this is where we need to, where engineers come who can scale up the things. And if you want to go to thousands of qubits, the wiring, I mean, in the first image, you can see all these lines. They are basically RF lines. So you'll have thousands of lines. And if you have such a computer, it will take like an entire room, right? So you want to miniaturize all of that. And for that, you need embedded systems, which you electronics people are really good at. And then comes electrical with circuit designs, measurement with VNA or your oscilloscope and all these different signal generators and different tools. Managing noise, because we need to reduce noise in order to improve the coherence of the qubit, basically the quality of qubit, let's say. And power losses. So, I mean, that is just given for any technology, right? The lower the power losses, the better the performance. And finally, the computer people, they can go a little bit higher in the stack. So for any technology, you would have the physical layer, which is made of transistors and registers and whatnot. Then you go one stack above, where you will have logic gates and registers and the memory units. So all of that will be developed by the computer science students. The architecture, algorithm, interfacing with different other processors. So Aritra was talking about this GPU analogy, where you will have a normal CPU and a quantum processor only for a niche application. So for that, you would need an interfacing. Who will do that? The computer scientists. And then the IT people will bring their expertise in cryptography and simulation, machine learning, algorithms. So, okay, with all of this, what do you see? You see that it's not so different from what you already learned, right? It's basically what the concepts, the subjects that are already a part of your syllabus, just that their application is towards the quantum technology. So this is something that actually you should keep in mind whenever you look at this technology, that how can you relate your knowledge, your expertise, and what you have learned towards a new technology that is emerging. Okay, and then we come to the part of education, right? So this is the million-dollar question. Okay, so all of this is nice, but since I'm entering into quantum computing, do I need to have the knowledge of quantum physics? So let me answer with some research, right? So there's this graph over here taken from this paper, where on the y-axis, there are certain professions charted out. And on the x-axis, there are a number of companies that are hiring in the near future. So you can see, I have marked these labels of electronics, computer, mechanical that are closely related to these fields. So you can pick your favorite. And you can see that there are already a lot of fields that are exactly your own field, right? So for example, control system engineer, circuit design, or algorithms developer, software developer. So these are the profiles that you normally apply for in your jobs. But now the application will be towards quantum technology, and there are hirings. So this is very important. Similarly, any technology would have the physical layer, which is made of transistors and registers and whatnot. Then you go one stack above, where you will have logic gates and registers and the memory units. So all of that will be developed by the computer science students. The architecture, algorithm, interfacing with different um, other processors. So Aritra was talking about this GPU analogy, where you will have a normal CPU and a quantum processor only for a niche application. So for that, you would need an interfacing. Who will do that? The computer scientists. And then the IT people will bring their expertise in cryptography and simulation, machine learning, algorithms. So, okay, with all of this, what do you see? You see that it's not so different from what you already learned, right? It's basically what the concepts, the subjects that are already a part of your syllabus, just that their application is towards the quantum technology. So this is something that actually you should keep in mind whenever you look at this technology, that how can you relate your knowledge, your expertise, and what you have learned towards a new technology that is emerging. Okay, and then we come to the part of education, right? So this is the $1 million question. Okay, so all of this is nice, but since I'm entering into quantum computing, do I need to have the knowledge of quantum physics? So let me answer with some research, right? So there's this graph over here taken from this paper, where on the y-axis, there are certain professions charted out. And on the x-axis, there are a number of companies that are hiring in the near future. So you can see, I have marked these labels of electronics, computer, mechanical that are closely related to these fields. So you can pick your favorite. And you can see that there are already a lot of fields that are exactly your own field, right? So for example, control system engineer, circuit design, or algorithms developer, software developer. So these are the profiles that you normally apply for in your jobs. But now the application will be towards quantum technology, and there are hirings. So this is very important. Similarly, this now addresses the question even more deeper. Same plot, but now it is versus skills, the number of skills. And the skills are broken down into non-quantum and quantum skills. And you can see that majority of the area is orange, right? Meaning non-quantum skills. So for most of the jobs, you do not need actual quantum skills. The quantum physics, the depth of quantum physics is needed. For example, if you're an error correction scientist, or of course, if you're an experimental or theoretical physicist, for those jobs, you will. However, if you are, let's say, if you're a data scientist or a software programmer, you will be working on a stack above. What will change is the limitations. What will change is the architecture. But you don't have to actually sit and study quantum mechanics in order to develop the technology. So it's like, to give you a very rough analogy, if you are from computer or IT field, and if I say that, oh, I want to develop a software for banking, does that mean you need to understand economics? No, you just need to know, okay, what are the constraints, and you will build it likewise. So this is how most of the companies are recruiting existing talent for an upcoming technology. And these are so this is a paper from 2021, which is a very recent paper. And these are surveys taken from actual companies. So these are some real numbers, not estimates. Okay, so to this point, I might have convinced you that, okay, you have some basic skills from engineering, and these can be already mapped to this emerging field of quantum technology, and there are companies that are hiring. How do I move towards this goal? How can I make a career towards it? So you are currently here, you are a bachelor, you have two options, right? Naturally, you can either go towards research, or you and then if you proceed towards research, let's explore one path. If you want to do a career in research, for example, like me or like Aritra, you need to do a master's in a deep technology, right? So, but what do I mean by deep tech is something that is not an augmentation of what you're already doing, but something completely different, where you have to learn the physics or learn some detailed mathematical models, etc. And then for that, you can see over here in the top right, there are so many countries that are offering a number of programs in the field of quantum computing. So UK has like 4 programs, United States has 11 programs of spread across various universities. Even India has 1 program, and that is at IISc Bangalore. So you can see that there are already master's programs that are building up for quantum computing, which are aligned towards the research track. And then with this master's, you can either go for a technical job, which will be an quantum engineering job, let's say, or you can go for a PhD, and then you can go for a more R&D job, which is like even more research focused, where you'll be solving some very niche problems that are pertaining to the technology. So this is the research track, and you can make your decisions likewise. Second is the industry track. So someone who is not so much research oriented, but just want to up their career profile, let's say. So one way is to do a master's of, which is a skilling master's. So the way I distinguish deep tech and skilling is such that in a skilling master's, it's a master's that is very much relevant to your field. Only that it has applications in quantum technology. So for example, you are an electronics engineer. You can do a master's in embedded systems and then specialize in your master's thesis or with internship towards quantum computing. So you always keep your window open, right? You can say that, yeah, okay, even if I don't go into quantum technology, I have a master's in embedded, I can go somewhere else. So you have a broad range open. With deep tech, it's a complete niche technology, and you're like learning a whole new skill set there. So most of the people also prefer the skilling masters because it's less intensive and more closely related to what they do. And then with that, they can get a tech job, or they can further think of starting their own startup and go into towards entrepreneurship. We saw earlier that there are already companies who are startups, right? Who started with some basic quantum skills, and then they expanded further. So this is one approach. Or second is certifications, which is the easiest approach, where you don't have to do much. You do whatever you're doing, and in a very small period of say few months, you can do small certification courses on quantum machine learning or quantum hardware, and gain some certificates that can enhance your profile. So these are only profile enhancement tools, which can be used for recruiting purposes, or if you already have a job, for promotion towards quantum technology. And then again, you can also think of startup if you already have enough experience. So this is a very rough career roadmap that I sketch. Of course, it's not rigid, because nothing is rigid, right? So you can always shuffle between here and there, and boundaries always are blur, but you have some idea now before you. So this is one thing. Second, right now, what would be a good track for you to begin your journey towards this technology? So I see that in the audience, there are many students who are in second year, who are in third year, and they don't have to think so much into future, right? Like whether should I do masters or PhD or whatnot. Right now, what can you do? So very simple. You can start with discussions. You can get in touch with people like us and have some chit chat about technology. Someone who knows something will tell you. If you know something, you will share. And it's what do you say? The more you discuss, the more you learn. Simple as that. And then you can attend certain workshops where you can get a little bit of hands-on on these kind of things. If you want to, so workshops are typically 1 or 2 days, 3 days. If you want a deeper grasp on the concept, then you can do some online courses, as said earlier, and then take some hands-on projects with some companies or with some academicians, and then go for internships under some companies which are like for 6 months. So you see the duration increases, and then of course higher degrees you can pursue, and then finally you will land up with a job in actual quantum technology. So this is how you can chart out the whole flow of your career path starting from now. So what would be a good platform for this? As it was mentioned in the introduction, we come from Q India, right? So Rishi, Aritra, I, and along with other people, of course, who are not right now in this call, we are all students, and we have started this initiative of Quantum India, which uh, currently is covering only these topics, but in future also we plan to cover internships and many other approaches. So it's a very long-term plan, but I mean, we have to start somewhere, right? So currently we already do workshops and online courses. We already have discussion sessions on our Discord channel. We also give some hands-on projects to students who are interested. And most importantly, all of this is free of cost. We do not charge anything because it's something that we personally like doing. And the initiative is completely based by students, so it's for the students, by the students. Students like who are masters, who are PhD, and who are again mentoring students from bachelors. And we have been doing it for, I think, more than a year, I should say now. Yeah, somewhere we started around 2020, end of 2020, and yeah, we are going quite strong now, and we are already growing in our initiative. And we have only sole one purpose, and that is to spread quantum awareness in India. So with this, I would really encourage you that if you are inspired by this talk given by Aritra and me, I would really encourage you to join our platform and make use of these different platforms, the different activities that we run. And just to throw some what do you say, word of mouth, there are certain testimonials given by people who have already been a part of this and they really enjoyed. And it's not something super rigid, right? So it's to have fun, to participate in certain discussions. Not only do you learn, even we learn by interacting with you, so it's always fun. And I would be really happy to see most of you being a part of this and benefiting from this opportunity as much as possible. So with that, I would end my talk over here. I'm sure that you're not an expert in quantum physics overnight, but you definitely learned something. Thanks a lot. And now we are open for questions.